Hi there and welcome. Thank you for joining me again. Today we're going to talk about solving linear systems by graphing. So we've been doing a lot of graphing of linear equations and we've been doing some solving of linear equations. Now we're going to kind of build upon that and we're going to graph what's called a system of linear equations. And a system of linear equations simply has two or more equations associated with it. And so let's just look at what a solution is. A solution to a system of linear equations is, first of all, the point where the graphs of the equations cross. So if we look at a graph and we look at where the two graphs cross, that point where they cross is the solution. Okay, it is also the point that makes both equations true when you substitute the values back in for x and y. And hopefully that kind of makes sense because we'll just look at this graph real quick here. This point is the solution, and so if we were to take this point and substitute it back into the equation, this point is on this graph, so it should work for that equation. And this point is on this graph, so it should also work for that equation. So it is that point that makes both of them true. If we were to try a different point, say some point down here, and plugged it into, of course, the equation for this line, it simply would not work because it's not on that line. So that would not be a true statement. So therefore, it wouldn't be the solution. So in our first example, identify the solution of the system of equations from the graph below. So we've already kind of talked about that a little bit. The solution is where they cross. And so if we look on the graph, if we go 1 in the x direction and 3 in the y direction, they cross right here at the point 1, 3. So 1, 3 is the solution to that particular system of equations. So just kind of in building to harder problems, the first thing you do once you graph them is identify what the solution is. And so that is what we've done here. Okay, moving on. Our next example, we're going to verify algebraically that we have found the correct solution. So again, we kind of talked about that on the other problem. If we find the point that is the solution and plug it into both equations, it should be true for both equations. If it's not true for one of the equations or both, we've found the wrong solution. And so maybe we need to go back and check our graphs and make sure that we have the right graphs. Okay, so we have the system of equations, y equals x plus 3, and y equals 2x minus 1. And the first point we need to check is the point 4, 7. So if we take 4 and 7, here is the y equals x plus 3. So we put 7 in for y. We put 4 in for x. So 7 equals 4 plus 3. 7 equals 7. So that is true. Okay, if we put it into y equals 2x minus 1, we have 7 equals 2 times 4 for the x value, minus 1. And 7 equals 8 minus 1, so that is 7 equals 7. That is a true equation also. And so the point 47 is a solution to this system of equations. Okay, so if we take the point 25 now, and we're going to use the same system of equations. So if we put 2 in for x, 5 in for y, we get 5 equals 2 plus 3. 5 for y, 2 for x. So 2 plus 3 is 5. 5 equals 5. So far, so good. It seems to work. But let's try it into the other one. 5 is equal to 2 times 2 minus 1. Well, that's 5 equals 4 minus 1. 5 does not equal 3, so therefore it doesn't work for this equation. So since it doesn't work for this one, it doesn't matter. If it doesn't work for either one, it's not the solution. So the point 25 is not the solution to this system of equations. Okay, next example, we're going to now kind of put everything together. Graph the system of equations and find the solution, and then verify algebraically that we've found the correct solution. So we have the equation x minus y equals 2, and 3x plus 2 equals 5y. So first, before we graph, I would say let's put them both into slope-intercept form. So here, if we take and subtract x from both sides, we get negative y equals negative x plus 2. To get rid of the negative in front of the y, divide through by -1. That means everything by -1, and we get y equals x minus 2. And so I have graphed the line here, y equals x minus 2. Remember that has a y-intercept of -2 and a slope of 1. So if we go up 1 and over 1, up 1 over 1, we have a couple of points. We just connect the line. Okay, for the other one, 5y equals 3x plus 2. To solve for y, we just need to divide through by 5. So we get y equals 3/5 x plus 2/5. So this one's going to be a little trickier to graph right from slope-intercept form. So let's find a couple of points on our graph. If we put 0 in for x, of course that's a y-intercept, 2/5. So we have the point 0, 2/5. So I have plotted that point on my graph. And if I put in 1 for x, well, 3/5 times 1 is still 3/5. So 3/5 plus 2/5 is 1. So we have the point 1, 1, which I've plotted on the graph also. So from there, since I found whole numbers for both of those, it's real easy to go from that point and use the slope. So from that point, I went up 3 and over 5, and I found another point on the graph that was a little farther away. Because these two are kind of close to try to, we may not be real accurate with our graph with these 2 points being so close together. So I wanted to find another point that was a little farther away so that we can make a nice line for our graph. And nicely enough, it did end up being on the other line as well, so it makes it real easy to find our solution also. So I connected all of our points, so we have both graphs here. And of course, we find that the solution is the point 6, 4. So now we need to, of course, check. So remember it said graph the system. We did that. Find the solution. We found that. That's 6, 4. Verify algebraically that we found the correct solution. So all we have to do is check now. So x minus y equals 2. Notice I went back to the original equations here. So put in 6 for x, 4 for y. 6 minus 4 is 2. 2 equals 2. That one works out. If we put in 6 for x and 4 for y into the other equation, 3 times 6 plus 2 equals 5 times y. So, or 5 times 4 for the y value. So 18 plus 2 equals 20. Well, 18 plus 2 is 20. 20 equals 20. So that point also, that works out for that equation as well. So it appears that we've done everything correctly because when we checked, it worked in both equations. So we can say with a lot of confidence, 6, 4 is the correct solution for this system of equations. Okay, just one more little piece of information to talk about here. Types of solutions for systems of equations. We have the first type of solution is an independent solution. An independent solution means we have one unique solution. So the graphs cross at exactly one point. And in our previous example, you saw that situation where our graph crossed at that one point. So I have a picture here showing you that we have two graphs that cross at one point. This is an independent system. A dependent system has infinite solutions. So in other words, both equations represent the same line. So if we have two different equations and we graph them both and they end up being the same line, we're going to have a lot of solutions. We're going to have infinite number of solutions. So that's a dependent system. So here I've kind of shown you, I drew two graphs overlapping. They're the same line. So this one is dependent. Okay, another term we might see is consistent, and consistent describes a system with at least one solution. So a consistent solution could be dependent or it could be independent because we need at least one solution. This has one solution, this has more than one solution. So both of these are types of consistent solutions or systems. So this one is both independent and consistent. This one is dependent and consistent. Okay, so if we think about kind of the opposite of that, inconsistent has no solutions. So in order for us to have a system with no solutions, the lines would have to be parallel. So I've shown you here two parallel lines, and that is inconsistent. So you might see some questions that talk about um, determine whether these systems are independent, dependent, or inconsistent. And so you would just have to look at the graphs and determine which one. So the one thing I want you to think about for tonight and coming into class tomorrow is how can we tell just from the equations of each of our two equations, how can we tell what type of system we have? So see what you can come up with for that and be ready to talk about it in class. Thanks for joining me today, and I hope to see you again soon.